Thanks. And in addition to thanking the other organizers, Caleb seems to have forgotten to thank himself. So thank you very much for putting this together. It's a pleasure to be here and a pleasure to speak to all of you. I want to talk about an area of my research that touches on multiple different areas of mathematics. We sort of saw some algebraic geometry and number theory this morning, which is great because I won't be able to cover those. But an area that interacts with some dynamics, some topology, some geometry. That's probably the best I can stretch it for today, but hopefully there's a little something for everyone. So I'm going to talk about, algebra. Let's start with algebra. I want to talk about some extra structure you can just put on an abstract group. So, definition. If you have a group G, left order, or a left invariant linear order, which I'll also often just write as an LO, on a group G, is, well, it's what you might think is, it's a total order invariant under left multiplication, so it's some total order less than, such that if I take some elements of my group, A and B, if A is less than B, then CA is less than CB for all elements A, B, C. Okay, so example. Maybe the most obvious example is if you take the integers as an additive group with the usual ordering on them. This is like a fact we learned in kindergarten, is that adding a constant to things preserves the notion of being less or greater. Okay. But there's lots more interesting examples that you can have. What if I take pairs of integers, all right, as my group? And an order I could put on this is kind of a lexicographic order, where you compare using the usual notion of size on the first coordinate, and then you, if they tie, then you compare the second, the same way you order words in the dictionary. There's many non-obvious examples on this group in particular, but I'll get to that later. Many other groups admit left orders. Okay, and often some constructions come to us from groups motivated that you see in geometric topology or elsewhere. So I know fundamental groups of surfaces. All right, so that's the fundamental group of the torus. Fundamental groups of higher genus surfaces also have left orders. 10 bonus points if you can give me one by the end of the talk. I would be delighted to know if you come up with a way that's not the one of two ways in my head I know how to do this, neither of which are very satisfying. Well, they're satisfying, they're just sort of too complicated. Fundamental groups of surfaces, free groups of any rank, fundamental groups of many other things like certain three manifolds, often for interesting reasons. Some of them, not all. I'll get to that later. And lots and lots of other things, but of course not all groups. Let's do a non-example. What is an obstruction to left orderability? Here's an easy obstruction. Any group with torsion. Right? Because for example, if I had some finite order element in my group, like, I don't know, G cubed was equal to the identity, then, if I had a total order of my group, right, identity would either be bigger or less than G. Let's pretend it's less. Okay? But I could left multiply this, and I get that G was less than G squared. So I could include this, and then I could left multiply this by G again, and I get that G squared less than G cubed. So I could say G squared less than G cubed. But oops, that contradicts transitivity of a total order. Okay, so that's not, any group with torsion is not left orderable, but torsion is not the only obstruction. Okay, so there's other sort of easy to write down obstructions, but a complete theory of when is a group left orderable or not is not something we understand. If we did, we would have some good answers to some unsolved problems. I will say though, for a fixed group, if you give me a presentation, this is in one direction a computable problem. So there is, I mean, literally it exists, there's a computer algorithm that will take a presentation for a group, and if the group fails to be left orderable, it will stop in finite time and tell you this group does not have any left invariant linear order. Certifying that a group is left orderable, though, is not a computed, like an algorithmically computable program, and you have to just produce one out of some magic. So why do we care about these? The historical interest in this kind of stuff was primarily algebraic. So this goes two ways. One is you might ask, like, what classes of groups admit these things? And then the other way is you might be like, oh, well, a group with this extra structure, what properties does it have? Okay, so in two examples, one in each direction, old work of Malsev, who did lots of work on nilpotent groups, in particular implies that torsion-free nilpotent groups any torsion-free nilpotent group has a left order. And in fact, you can say much, much, much more about that. So that's something about the structure of your group, tells you if you have like some of this extra stuff. In the other direction, what's a good example? Yeah, so every group, so this is a, I don't know, little proposition or a toy theorem that you can prove if you know the definitions of everything that I'm doing. Every group with a left order satisfies a famous conjecture, which is still open, Pulaski's zero divisor conjecture. Perhaps some people in the audience know this. So this is a conjecture that says if you have a torsion-free group, then, and you take any field, then the group ring K of G should have no zero divisors. This is an open question, but it's true for left orderable groups, which are, as we saw, a special class of torsion-free groups. So this goes both ways, and if you're really into groups, this is a nice piece of extra structure to add. But I'm not really a group theorist, despite appearances so far. I come at this from a new take. There's been kind of a recent resurgence of interest in this. I forget, you can't see the top thing if it's whiteboard. That comes from two different things. One is connections with the dynamics of group actions. On low-dimensional, basically one-dimensional manifolds, but sometimes you can push this to higher dimension. And two, examples coming from or connections with, I'll say connections with, topology and maybe also geometric topology. So, what's my goal in this talk is, I'm going to prove theorems only not due to me, only kind of some folklore things to help you get thinking about this stuff. But I'm going to outline both of these connections, why we're looking at orderable groups these days, why this is a fruitful area of research, and by the end kind of paint a little picture of a program that actually quite a good group of researchers is currently working on. And I think has a lot of promise and a lot of open and accessible questions. Okay. And the other thing is that you should interrupt me at any time with questions. This is done very well in the back and forth. All right. dynamics. Okay, what is dynamics? Let me give you my favorite definition of what is dynamics, which I believe comes from John Milner. Dynamics okay, what is the study of dynamical systems, very broadly speaking? It is the study of the qualitative behavior of transformations under iteration. If you want to learn one thing from my talk, take away this is a beautiful definition of a field of math. It took me a long time trying to phrase this myself before I hit upon this, and I was like, aha. So in other words, what you're taking is maybe you have a space, topological space X, and you take some, I like my transformations to be invertible and respect the topology. So you take some homeomorphism of your space, and you look at not just F, but also iterations of it. So F composed with F. Wait, let me write this, let me make this easier. I'll write it as F squared for F composed with F, and then you look at F cubed, and then you keep going, but you'll also look at F inverse, and etc., and you iterate back all powers of the inverses, and you try and say, like, how is this behaving? Is it stretching things? Are it limiting onto something? Are there fixed points that aren't moved? Are there periodic orbits? What can you say qualitatively about something like this? Okay. But there's a better way to capture this, right? This is actually, if I look at all powers in both directions, I'm really looking at kind of a integer generated by one element subgroup of homeomorphisms of the space. I'm trying to say, like, what does this subgroup look like? Or what does it do to my space? So more generally, okay, so that's your basic object, or more generally, you could look at any subgroup of homeomorphisms of a space and try and understand the qualitative behavior of the transformations in this group. So dynamics is really just the study of subgroups of homeomorphisms of some topological space in its most broad sense. And of course, this is already, I frame this so broadly that it's already interesting if your space is one-dimensional. Let's say like the circle or the real line, I mean, it's already interesting if it's a Cantor set, but let's talk about dynamics on the real line. And this is what ties us in with left orders. Here is a proposition. Okay. If I want to understand groups of homeomorphisms of the real line, any such group is left orderable. My lines come with an orientation. I want them these to preserve orientation. Otherwise, I'll have torsion, right? You could send x to negative x, that has order 2. So I'll say orientation preserving homeomorphisms of the line is left orderable. It admits an order invariant under left multiplication. Well, to prove this, actually I only have to show that this giant immense group is left orderable because left orders pass to subgroups, right? That should be clear from the definition. Okay. So I'm going to show that this giant, uncountable, but very, well enough behaved group is left ordered. Okay, so I'm going to construct left order on the group of orientation preserving homeomorphisms of the real line. Okay, so I have to tell you, define a left order by saying F is less than G in my order. Define order by if, well, I have to pick something. I'm going to say if f of 0 is less than, in the usual order on the real numbers, g of 0. because the operation in this group is composition. And if I left compose with something else, because everything preserves the orientation of the line, this implies that if I h composed with f of 0 will be less than h composed with g of 0. If one points to the left of another on the line and I change coordinates on the line without flipping anything, their images will still be one to the left of the other in the same order. Okay? So this is great. I satisfied my condition of being left multiplication invariant. Oh, except I've screwed up here. I've only sort of defined a partial order, right? If f of g of 0 is equal to g of 0, I don't know how to decide who's bigger. Right, okay, so what should I do in that case? Well, let's erase while we think about it. All right, well, maybe I should check at a different point, right? If these agree, if these say it sends 0 to the same place, then maybe I should check what they do to 1. Okay, maybe they both fix 0, but they disagree on where they said 1, and then I could compare and I'd know what to do. But if they agree at 2 points, then I'm still stuck, so I should maybe check the third point, and I could do that. And formally, if I really want to do this properly, I should start off by, so let's revise this. And make sure that I will eventually decide in this procedure. So this was the right idea, but I'm going to revise and edit this and say instead if I need some setup, first maybe enumerate a dense set of points. So maybe you enumerate all the rational numbers on the line. Q1, Q2, Q3, on and so on forever. And then say that f is less than g as a homeomorphism if on the first qi such that f of qi is not equal to g of qi. So on the first point where they disagree in this ordering, we have, I don't know, f of qi is less than g of qi. And you can check that this is invariant under left multiplication, which here is post-composition. All right, so that's a construction of a left order, and that proves my proposition. Questions? Did anyone get lost along the way? It's kind of a miracle, and it shows you that actually it's not like there's one, there's many different choices I had here. I started by enumerating a dense set, and I could have taken any dense set and enumerated it in any order, and these will all give you different orders on this group. So many questions, many options. Fascinatingly, this is not everything you can do, and we actually don't know how to describe all possible left invariant orders on this group. That is an open question, which almost had a published false answer. So I very happily hear, if you get bored of my talk, any examples that you could come up with that don't come from this kind of method. All right. Okay.
What do you need dense here?
If I miss something, I'll only have defined a partial order, because I could have two homeomorphisms that, if you only take, say, if you miss an open interval, you could have two homeomorphisms that are identity off that open interval, and you'll never see how they disagree from the identity at all. You'll never decide whether it's bigger or less than the other. Yeah. Okay. But actually, better than this, left orderable groups are precisely, in some sense, groups that act on the line. Okay, so here's kind of a converse. I'm going to state this as a theorem. It's kind of a folklore theorem. If you take countable groups, okay, so for instance, anything finitely generated, fundamental groups of nice spaces, things you might be interested for other reasons in your life. For a countable group, having a left order is equivalent to acting on the line by homeomorphisms. So this is equivalent to G embedding as a subgroup of homeomorphisms of the line, preserving orientation. Moreover, for each order, there is a canonical as canonical as you can be, so up to conjugacy, or up to change of coordinates on the line. Action, so I'll write this as, I don't know, rho seems like a good name for a representation. From G to the group of homeomorphisms of the line. And in fact, it has an amazing property that there's some point on the line that has trivial stabilizer and ends up, its images under elements of your group are ordered just the way elements in your group are. So there's a great way to go from a left order on a group to an action of that on the line. So let's actually prove this theorem, because we already did one direction of it. We showed this, L subgroups of here, every group that acts faithfully on the line, have left orders. So we did this one already. Let me do the other direction, and I'm going to prove the moreover part. Okay, except I won't. I'll just tell you you're supposed to believe it's canonical, just to save us some time. So let's go this way. All right. So given a countable group with order on it, I want to tell you how to think of this as a group of homeomorphisms of the line. It's already a group of homeomorphisms of an ordered space, right? G has a total order on it. G acts on G by left multiplication, so it's preserving that order. So if I could do something like put G inside the line in an order-preserving way, then left multiplication, I try and extend that and get some kind of action. And that's exactly what we're going to do. Okay, so let's do this. I'm given this. First, I'm going to put G inside the line in an order-preserving way. So let's do this very naively. My group is countable, so I'm going to enumerate G, G1, G2, G3. All right, great. And then I'm going to embed it in the line. Preserving the order. And I won't just do this any completely random way. I'll be a little careful with it. And it's maybe not obvious the first time you see this pass quickly before your eyes that this is important, but if you work through the details, you'll appreciate that I was careful. So I'm going to embed this in the line by putting my first element wherever I want. G1 goes here. All right, I look at my next one, G2. If G2 is greater than G1, I will put it on this point 1 to the left, 1 to the right. If it were less, I would put it 1 to the left. All right, now I look at G3. It's either to the right of everything I've already placed, so it's either greater in my order on my group than everything I've already placed, in which case I'll put it 1 to the right. It's less, in which case I'll put it 1 to the left. Or there's a pair that I've already placed where it's exactly in between in my total order. Let's pretend that happened. So maybe G1 was less than G3 was less than G2 in my group. In this case, I will take the midpoint of this interval and label that with G. I'm choosing midpoint so I don't accidentally ever like make things limit onto things in an artificial way. I'm only doing that when that's sort of forced by the order type of language. All right, and then maybe I had a G4 and G4 was less than everyone, so I'll put it one to the left, etc. iteratively. All right, so that was the picture. And I'll just summarize that by saying do it iteratively. Great. Question? Okay. Okay, great. So what's going on is, okay, so G acts on itself by left multiplication, preserving the order. So I think of G acts on this subset of the line. Okay. So left multiplication of G on G extends to an action, in fact, by homeomorphisms of on not just the points in this embedding, but actually on the closure. And this is the only part where I'm asking you to not check all, where I'm not checking all the details on the board. The point was I used this sort of canonical procedure where I always just pick the midpoint if I had to go in between. So any kind of limit points I see, things in the closure, are defined right out of the order of my group. Okay, great. So now I've got homeomorphisms on some closed subset of the line. And in fact, it will tell me exactly how to extend to the rest. Okay, so there's a canonical way, say, to extend an action of a group on a closed set of the line. If I have a complementary interval to my closed set, say maybe this one never got filled in with any points, and I want to left multiply by some element, maybe it was G100. I know where its endpoints are supposed to get sent. Okay, somewhere over here. And there's a unique affine map that sends this interval to that one. So that's a canonical choice to say, what does G100 do to a complementary region? Okay. So extend, say, e.g. by unique affine maps on complementary intervals. Cool. If you believe my assertions, we've just built an action of your group on the line by homeomorphisms, and better yet, if element G1 was actually the identity, say, whichever one was the identity in your group, the orbit of this under your group, well, that's just, if I hit identity but G3, that'll give me the point labeled by G3. I concocted this, so it's just doing left multiplication. And I lined these points all up in the order they were originally. So I can think of the orbit of this point, or the labeled points in here, as, well, their order agrees with the usual order on my group. So this has lots of nice properties. Okay, so why I wanted to show this is it's an interesting way to build left orders. It can help you solve some of my problems from before. I said there was a left invariant linear order on the, let's say, a free group on 2 generators. Great, how do you build one? Okay, just take 2 homeomorphisms of the line that are completely unrelated and don't satisfy any relations. Great, that's a free group. Use this process. There are also, as we'll see later, studying the algebraic properties of left orders can help us understand the dynamics of groups of homeomorphisms. That's a little subtle, so before I get into that, I promised you a kind of a number 2 reason why you should care. Okay. So this was connections with dynamics. I think 2 was connections with examples and things from geometric topologies. So let me just spend like a little minute on that. Because this is, some of the area that's really dear to my heart here. Maybe I'll just give you one connection with geometric topology. And yeah, I want to focus on I'll just, in the interest of time, just give you one. And this comes from the study of foliations on three-dimensional manifolds. All right, so what's a foliation on a three-manifold, or a codimension one foliation is the examples I'll be looking at. A foliated three-manifold is a space that is locally modeled so a three-manifold is locally modeled on R3. You have nice little charts. A foliated three-manifold is locally modeled on R3 with its horizontal planes. Okay, so let me draw a little cartoon. I have a horizontal plane in R3. I have a whole family of them, one at every height. Right. I have a complementary direction. So what does that mean? It means charts for my three-manifold go to open regions of R3, and they preserve the notion of horizontal. Okay, so they don't have to glue up everything isometrically, right? Scaling the z direction by 2 sends horizontals to horizontals, so that's like gluing that like in half. Okay. But it's a notion of a complicated topological space that's pieced together out of, well, it's like the simplest example of a stratified space, right? You have a kind of a distribution of 2 planes at every point. You're sliced up into slices. And if you ever, it looks like this might constrain the topology, which it does, but you can still have very many interesting and fascinating examples. I think the picture to keep in mind in your head is, I don't know if you ever have like a stripy shirt that's like actually well tailored, and they like line the stripes up going this way to the ones going down the sleeves. You've built an object that's topologically non-trivial. It has some holes in it, it has some shape. That's completely covered by, I didn't wear my stripy shirt today, I don't know what I was thinking, well, here instead of 2 planes, 1 planes at every point. Okay, so here's the question. You give me a manifold and ask, like, does it admit a foliation, or a particularly nice one, or one with extra properties? Is there some topological constraint on your space that prohibits this extra object from existing? That's a very basic question in three-manifold topology. And, all right, so what's the connection with all of this seemingly unrelated stuff I was talking about a minute ago? All right. I want us all to remember this theorem, so I'm specifically erasing it last. That's a hint for the upcoming quiz. All right, here we go. Hope you cheated and wrote it down. All right, so often, not always, okay, but often, if you have such a foliated space, and you look at its universal cover, okay, you actually really do get R3 with horizontal planes. Up to homeomorphism. Okay, so this isn't always true, but under some mild other assumptions of topology, you'll get something like this. All right. Okay. Well, on this, I have an action of the fundamental group by deck transformations on the universal cover. And my universal cover, and downstairs, you know, my foliation is something that happened downstairs. Whatever happens upstairs is going to be a lift of that. It will preserve the horizontal planes. Okay? So this says sending horizontal to other horizontals. What does that give you? In other words, this gives you a notion, an action of the fundamental group on the z coordinate. Right? If I thought of collapsing each one of these horizontal planes to a point, they're just shuffled around, I get an action on the line. So, a way of putting the fundamental group into the group of homeomorphisms of the line. If my manifold was oriented, or my foliation was what's called co-oriented, I'll have that orientation preserved. And what did we just see? That gives you a left order on your group. All right. And the amazing thing about this is that the question, does your three-manifold admit a nice-looking foliation, where nice is some complicated adjectives that topologists care about, does it admit a nice-looking foliation? That is a hard question in general to answer. But the first person who realized, I think it was David Calgar and Nathan Dunfield, saw this connection and realized they could reduce this to a question about left orderability of a group. And that's something that you can ask your computer at least to tell you no about, if not yes. And they were able to give the first examples of some very small, uncomplicated three-manifolds that failed to admit this kind of extra geometric topological structure. Okay? Just by giving a presentation for the fundamental group and plugging it into a computer. So that was a beautiful insight. I'm brushing over some of the details. That proof is actually tricky and hard and relies on some three-manifold topology to ensure that I'm not completely bluffing here. But it was a beautiful idea to use this. Some of you may have heard, so I owe something maybe to the analysts or more the analytically minded among the people in the room who have been left out so far at this conference. There is a famous, or these days famous, conjecture that also relates left orderability of fundamental groups of three manifolds to something more analytic, namely their Hegarde-Floer homology. So some people may have heard, and if not, I am about to say some fancy words which you should not pay too much attention to if you don't care. So there's kind of a hot conjecture at the moment that says there's a correlation between manifold, a rational homology sphere is the remaining open case, being an L space, so having the simplest possible Hegarde-Floer homology, admitting a particularly nice kind of foliation, and having a left orderable fundamental group. So it's conjectured that being an L space, where your Hegarde-Floer homology is simple, means that you don't have that much interesting going on, and particularly you don't have a left orderable fundamental group, and you don't have a nice looking foliation. This is still open, and yet in all cases, it has been checked in lots of cases, and it is so far always, this correlation holds in all directions we can possibly check. So that's an interesting and fruitful area of research. But what I want to do, I think, in the last 15-ish minutes of the talk is sort of bring this back around. I gave you some connections with different areas, and I want to sort of tie it all together and say, in what aspect am I working on this problem? So that's 1 and 2. I guess 3. Let's kind of tie it all together. Questions so far before I try and bring us on to the next? Yeah.
So you mentioned that the condition for the previous theorem that G must be countable. I just want any result for uncountable groups.
So I I gave you an example of an uncountable group that was left orderable, namely the group of homeomorphisms of the line. Okay, great, there's lots of examples. However, there are also examples of uncountable, same, continuum cardinality, left orderable groups that do not act faithfully on the line by homeomorphisms. So, here's a crazy, interesting one. If you look at the group of, say, germs at 0 of homeomorphisms of the line that fix the origin. Okay, so you look at it, this is looking like basically the other group, except I said like now up to equivalence, where you just look at the germ. That has a left order that you can define sort of similarly to our check which points move in which direction, but now you need sequences of points. Okay, that's a group as an abstract group that does not act faithfully on the line by homeomorphisms. So somehow, it's not even just that this quotient doesn't have a section, it's that there's just no abstract action of this group at all. Okay. So, that's something I proved as a grad student, actually, a question of Anders de Vos. There are simpler examples you can come up with. I think we understand the situation a lot better now. Okay. Other questions? Right, I guess the point of that was countability, like let me do this little trick to do the definition, but it actually was essential to the result. Okay, so let me tie this together. I want to put together kind of the dynamics of actions and this idea that we should have something to do with topology. I'll get a little more space there. And I'm going to explode all your minds and tell you that actually, if you want to understand left orders on a group, let's call LO of G the set of all left orders on your group G. Okay. This is not just a set, actually it has a very nice topology. This is a topological space. And that topology is going to actually tell us a lot about the algebraic structure of your group and the dynamics of actions, and special examples often correspond to sort of interesting points in there. Okay, but first, not to get too far ahead of myself, why is this a topological space? Well, you could think of a left order. An order is picking out a left order saying who's bigger than who. Well, it's equivalent to just specifying the set of elements that are bigger than the identity. Because if you want to know whether, I don't know, f is less than h, you're left multiplication invariant. So that's the same thing as saying that the identity is less than f inverse h. Right? So I just actually have to tell you who's bigger than the identity, and I've given you everything. Okay, so erase the scratch work. It's a topological space. It's a subset. Well, I guess the space of subsets of your group, which all right, I don't know, G to the 0, 1. Because we like functions from G to choices, right? This is just your posets. Okay, so great. Another way you can think of this is two orders are close by. If I take the large finite sets of elements of my group, and comparison-wise, they agree. Okay, and everything on a large finite set. Let's do some examples to get this in your head. All right, so here's a quiz. All right, warm-up question. What is the space of left orders on infinite cyclic group? Oh, wait, I'll give you a hint. Is this space finite or infinite? Finite, great. Okay, how many points does it have? I heard the answer, but no one's brave enough to out themselves. Just say it louder, but cover your mouth and I won't see who's saying it. 2. Okay, great. Yes, this is 2 points. Here's the proof. I have 0, that's the identity element. Let's ask what's up with 1. All right, is 1 bigger than 0? Could be. All right, now I left multiply and I know that 2 is bigger than 1 and on and on and on, and minus 1 is less than this. Okay, great. Okay. Or it could be that the world is backwards and 1 is less than 0, and now I'll left multiply, namely adding 1, and then this will determine the rest of it. And minus 1 will be bigger than 0, and it's like we just sort of stood on our heads and everything was backwards. Great, okay, so this has 2 points, and the special property, right, that like, it only took me one inequality, namely this one, to determine the rest of the order. Okay, and generally, an isolated point of this space means there's a finite collection of inequalities that determines the rest of it. Let's do something a little more complicated. What is this? I gave you a special example of a point in this place that was a lexicographic order, but I claim that this is actually homeomorphic to a Cantor set. It has no isolated points. And it has uncountably many points also. That's kind of nuts. Let me give you a sketchy sketch of how you show this, because it's beautiful and a little bit enlightening. And I think it's good to leave a talk with some idea in which you can sort of fill in the rest of the details on your own. So here's the idea. To specify a left invariant linear order in a group, I have to tell you which elements are supposed to be bigger than the identity. And I can't just pick a completely random subset of my group. If I have 2 things that are positive, bigger than the identity, and I add them together, or I apply my group operation, the result should be bigger than the identity. This is the same way positive numbers work among the integers. Okay, sum of 2 positives is positive. All right, so it has to be closed. This has to be a semigroup, if you like. All right. Similarly, if I take the inverse of any element in this semigroup, it should not be in the semigroup. All right, because then I was supposed to be able to multiply one and the other. I would get the identity, not something bigger than the identity. All right. So in fact, those conditions are actually equivalent. You can check if I specify a semigroup so that it and all its inverses partition the group, that's like specifying a left order, and that's exactly what you need. So I just need to find ways to take pairs of integers. Let me draw them as the integer points in the plane. So maybe here's like 0, 0, and there's 1, 0, etc. All right, I have to take all those points and tell you which ones of them I want to declare to be bigger than the identity element of this group, 0, 0, and which ones I would like to be less. Well, here's a way to do it. Let's just take a straight line through the origin and go like this and say these ones are positive. Any point up here will be greater than the identity, and conveniently its inverse, the thing you add to it to make 0, will be on the other side, and I'll say that the other side is the stuff that's less than the identity. All right. And you can check that this works. If I didn't hit any points with this line, say I chose it to have irrational slope, I've partitioned it exactly. You can check that the sum of 2 vectors on this side, I mean, it's what it means to be, I guess, a convex subspace. All right. So this specifies line of irrational slope specifies a left order. If I chose something of rational slope, all right, like something, I don't know, maybe this one of slope 0, that's a terrible idea. All right, I could still do the same thing, like half of this. All right, should be the stuff that's positive, except I haven't really told you what to do with any point on this line. Okay. So instead, I should further specify half of it to be positive and the other half to be not included. These will be the things less than the identity. And play the same game. Okay. But for here, if I had rational slope, I had two choices, right? I could have chosen this to be the positives or that one. So, slope, a rational, gives you two choices. All right, so what have I done? I've taken the circle of directions of slopes, and I've replaced every rational point with actually 2 points. Okay, that you can convince yourself is a description of the Cantor set. You take, say, the real line or the circle, and you replace every rational point with 2 points. Okay, and you check that the topology on here, agreeing on finite sets, is the same topology you were doing there. All right, so that wasn't meant to be all the details all the time, but hopefully enough for you to play with it and reconstruct this. There's lots and lots of groups where if I write down what is the space of left orders, I don't know, how about the fundamental group or the surface? I said this had examples, but we don't know what they are. I don't know if this space has any isolated points or not, and nobody else knows either. Could be Cantor set, we don't know. And if you fill in any kind of group you want, chances are we don't know very much about how, even if it's a group you're motivated to study, we can't say very much about this. Okay. But often, tools from dynamics can actually help us understand this kind of algebraic question. What are all the left orders of a group? Okay. So here's a nice example. If I take a free group, let's just do free group on 2 generators. This one's also a Cantor set. Okay. And in this context, it ends up being equivalent to saying there's no isolated points. And you can prove this using dynamics. So using dynamics of actions on the line. So since I'm almost out of time, I will finish by giving you a completely fake proof of this, but it's morally true. All right, and I think a good indication there's a lot of promise in finding this correlation. So all right, where we are now, before I fake prove this, I want to tell you what's really going on. So the kind of research program of the moment which I'm co-organizing a workshop on this summer, that is how of the moment it is to relate, there should be some kind of three-way dictionary that relates the algebraic structure of your favorite group, some fixed group G, okay, with the topology of the space of its left orders and the dynamics of actions of G on the line. Okay, whether you have examples that are easily perturbed, a small change in initial conditions, a small change of, say, what the generators of your group does, gives you qualitatively very different behavior. And things that are stable, where small changes don't do very much. Okay. Conjecturally, that kind of stability versus instability phenomena here should relate to having isolated points or a large accumulation points in this space. And we hope to be able to detect this on an algebraic level. This error was already something people spend a lot of time about. It's a rich interplay between algebraic constraints giving you dynamical constraints. this has received a little attention, and we're trying to find new ways to kind of use the whole triangle of ideas to inform one area over the other. All right, so let me conclude with a 1-minute fake proof of this statement as a way to illustrate how you might, I know the algebraic structure of my free group, no relations, great. I want to understand the topology of this. Let's go through actions on the line. All right, so we showed back at the beginning that if I have an action of my group on the line, I can regard it. So let's do my free group. But if I put this inside of homeomorphisms of the line, right? This, because this group is left ordered, this will give me a left order on the group. And conversely, if I have a left order on my group, I can build an action on the line. All right, these are wavy arrows because it's not like there's a perfect bijective correspondence. There's a canonical way to go back and forth. Okay. Well, I want to show that this space has no isolated points. So take your favorite left order, do this. Now I have an action of a group on the line. This group has no relations to satisfy. I just have two homeomorphisms. Change one a little bit. Change it off the complement of a big compact set. Do some small thing that doesn't mess it up very much. I will change the action, and then I should go back and see what new left order I got. If I change it somewhere only outside of a large compact set, I will not have changed it very much, and will still, the order I get will still agree with the original one on a big finite set of elements. And that's basically a proof. All right, so this, since F2 has no relations, it's easy to perturb and get a new but close order. So that's an imprecise version of the argument, but one that can be made precise in this case, and one that, you know, can extend to some other groups that we're very curious about. Not quite this yet, but other kind of nice groups from topology that we care about. To talk about the topology of this space and sort of the influence of the algebraic structure of your group here. I think that's a great place for me to stop. So I'll end there. Thank you very much.
All right, we have a few minutes. So any questions?
Is it a functor? From the category of group, it's in the category of topological spaces. And if yes, what are the properties of that functor?
It's not really.
It should be, you know?
Well, if you have, so the problem is it doesn't behave well under like group morphisms. So
Does not.
No, right? So you can have, in fact, see, neither with inclusion or taking quotients or something like this. So you can have what do I want to say? There are groups that have finite index left orderable subgroups but are not themselves left orderable. Okay. So you can go from having something with, you know, so there exist torsion-free groups which have Z cross Z as a finite index subgroup. So something with a rich space of orders. You enlarge your group slightly, and you get that the space is empty.
Let's say, change it a little bit. Maybe you shouldn't take all homomorphisms. Maybe there are some homomorphisms of groups which actually lead, you know.
Yeah. So the nicest way this behaves, and maybe this is what you want to formalize, is that if you have an extension of, I don't know, what do I want to include? H, P, and then some quotient Q. If you have an extension of a group, a left orderable group by a left orderable group, the extension is left orderable in a canonical way that respects the left orders on these two. So that's the best way it behaves.
But it's not the subcategory. It's not just sort of.
Yeah, I don't know how to categorize it, but we, you know, I haven't that is not my instinct of what I do when I see a group. I'm like, let's play with examples, not like, let's try and figure out whether this is a function somewhere. So we should talk about whether that works. Yeah.
Speaking of examples, I can't decide if the ring of p-adic integers is left orderable. Is it easy to see when you're in abelian group?
Abelian groups are all left orderable, yeah.
Yeah. My horrible idea is to choose a Z basis, which would be uncountable, and then axiom of choice it and do some sort of horrible lexicon.
Yeah, that'll work.
Okay.
But we can probably do better. But like, that'll work, yeah.
Any other questions? All right, let's take our speaker again. Since I will not see all